Imagine drifting through an endless sea of darkness, punctuated by glimmers of starlight, each a silent testament to the vast, mysterious cosmos. As you float among swirling galaxies and whispering nebulae, a profound enigma beckons. What is the invisible force that is accelerating the universe's expansion? In the stillness of the cosmic night, picture galaxies as luminous islands receding into the distance, their light stretched thin by an ever-expanding fabric of space. This isn't merely a scene of beauty, it's the signature of dark energy, a force so elusive yet so potent that it propels the universe apart at an unimaginable pace. Have you ever found yourself wondering, how can something we cannot see control the destiny of the cosmos? Tonight, as we journey into the universe's darkest mysteries, we invite you to ponder these questions in a state of serene contemplation. What if the key to our cosmic fate lies hidden in the delicate balance of energy and space, a dance choreographed over billions of years, now echoing through the silent void? In this exploration, we will gently peel back the layers of cosmic history to reveal the story of dark energy and its role in cosmic expansion. From the brilliant birth of stars to the gradual, relentless pull that drives galaxies apart, the universe whispers secrets that are both humbling and awe-inspiring. So, take a deep breath, relax, and allow your mind to wander through this celestial narrative. Let the majestic expanse of the universe and the mystery of dark energy lull you into a state of wonder and introspection. Welcome to 1 hour of the universe's darkest mysteries, dark energy uncovered to fall asleep to, where every star, every galaxy, and every silent void invites you to question the very nature of reality. Dark energy. It's a concept that seems almost too strange to believe. A mysterious force, invisible and intangible, that makes up about 70% of the universe yet remains one of the greatest puzzles in modern science. But despite its elusive nature, dark energy holds the power to shape the very fate of the cosmos. Tonight, we embark on a journey to uncover the secrets of dark energy and its profound role in the expansion of the universe. We'll delve into the latest observational evidence, exploring how distant galaxies and their motions offer clues to its existence. We'll also discuss the theoretical models that scientists use to make sense of this mysterious force, and how it could influence the future of our universe. But this video is not just about understanding the science. It's also about relaxation, allowing you to sink into the rhythm of the cosmos and explore these mysteries at your own pace. As we journey through the heart of the universe, you'll have the time and space to reflect, to let go of the outside world, and to immerse yourself in the cosmic story that has unfolded over billions of years. So, whether you're here to ponder the deepest questions of existence or simply to relax with the vast expanse of the universe, this will be a long, meditative experience, perfect for deep contemplation and soothing rest. In the early 20th century, astronomer Edwin Hubble made a groundbreaking discovery that would forever change our understanding of the universe. By observing the light from distant galaxies, Hubble noticed a fascinating pattern. The farther away a galaxy was, the faster it appeared to be moving away from us. This observation led to the formulation of Hubble's law, which states that the recessional velocity of a galaxy is directly proportional to its distance from Earth. To comprehend this phenomenon, we turn to the concept of redshift. When a light-emitting object moves away from an observer, the wavelengths of its emitted light stretch, shifting toward the red end of the spectrum. This shift indicates that the object is receding from us. Hubble observed this redshift in the light from distant galaxies, providing compelling evidence for the expansion of the universe. To visualize cosmic expansion, consider the balloon analogy. Imagine drawing several dots on the surface of a deflated balloon, each representing a galaxy. As you slowly inflate the balloon, the surface expands and the dots move away from each other. Importantly, from the perspective of each dot, all other dots appear to recede, illustrating that every galaxy observes other galaxies moving away from it. However, it's crucial to note that this analogy has limitations. In our three-dimensional universe, there is no central point of expansion, and the universe is not expanding into pre-existing space. This analogy serves as a helpful tool to grasp the concept of cosmic expansion, though it simplifies the complexities of our actual three-dimensional universe. Hubble's observations, coupled with the concept of redshift, have provided a profound insight into the nature of our universe, revealing that it is not static but dynamic, expanding over time. In the early universe, gravitational forces began to slow the cosmos' initial rapid expansion. However, approximately 9 billion years ago, an unexpected phenomenon emerged. The expansion of the universe started to accelerate. This acceleration is attributed to a mysterious force known as dark energy, which counteracts gravity's decelerating effect. Observations of distant galaxies and cosmic structures indicate that the universe's expansion rate is not diminishing but is, in fact, increasing. This acceleration suggests the presence of a force that permeates space, exerting a repulsive effect that drives galaxies apart. Dark energy is the term coined to describe this enigmatic force, though its exact nature remains one of the most profound mysteries in cosmology. Recent studies have revealed discrepancies in measuring the universe's expansion rate, known as the Hubble constant. Data from the Cosmic Microwave Background, CMB, suggest one rate, while observations of nearby galaxies indicate a higher rate. This Hubble tension implies that our understanding of cosmic expansion and the role of dark energy may need refinement. As we delve deeper into the cosmos, the interplay between dark energy and cosmic expansion continues to captivate scientists and enthusiasts alike. Understanding this relationship is crucial, as it holds the key to predicting the universe's ultimate fate, whether it will expand forever, collapse upon itself, or reach a steady state. Dark energy is the term given to the mysterious force that permeates all of space and tends to accelerate the expansion of the universe. This enigmatic energy counteracts the gravitational pull of matter, causing galaxies to recede from each other at an accelerating pace. Despite making up about 70% of the universe's energy content, its exact nature remains unknown. In the late 1990s, two independent research teams, the Supernova Cosmology Project led by Saul Perlmutter and the High-Z Supernova Search Team led by Brian Schmidt and Adam Rees, made a groundbreaking observation. They studied type Ia supernovae, which are stellar explosions occurring in binary systems where a white dwarf accretes matter from a companion star until it reaches a critical mass and detonates. Due to their consistent intrinsic brightness, these supernovae serve as reliable, standard candles for measuring astronomical distances. By comparing the observed brightness of these supernovae to their known intrinsic luminosity, the teams determined their distances. They found that distant supernovae were dimmer than expected, indicating they were farther away than previously thought. This observation suggested that the universe's expansion was accelerating, not slowing down as had been assumed. This discovery was pivotal in identifying dark energy as the driving force behind this acceleration. For their pivotal role in this discovery, Perlmutter, Schmidt, and Rees were awarded the 2011 Nobel Prize in Physics. Their work fundamentally altered our understanding of the universe, highlighting that the cosmos is not only expanding but doing so at an accelerating rate due to the influence of dark energy. This revelation has profound implications for cosmology, prompting ongoing research into the nature of dark energy and its impact on the universe's ultimate fate. Dark energy is perhaps the most elusive force in the universe. Unlike regular matter, which we can observe and study, dark energy doesn't emit light or radiation. It doesn't interact with matter in any direct way that we can detect. This makes it incredibly difficult to study and even harder to understand. It seems to permeate all of space, existing everywhere but remaining largely invisible to us. The only way we know that dark energy exists is by observing its gravitational effects. Through its influence, dark energy causes the expansion of the universe to accelerate over time. If you think about it, this is quite the paradox. Something that we can't see directly is responsible for one of the most significant and observable effects in the universe. One of the earliest and most famous explanations for dark energy comes from Albert Einstein. He introduced the concept of the cosmological constant, lambda, which he initially added to his equations of general relativity in 1917. The cosmological constant was meant to account for a static universe, which was the prevailing belief at the time. However, when it was later discovered that the universe is actually expanding, Einstein abandoned the idea, calling it his biggest blunder. Yet, in the 1990s, when dark energy was discovered, scientists revisited this idea. The cosmological constant suggests that dark energy is a constant force that fills all of space and remains unchanged throughout time. It's a sort of energy of the vacuum, an inherent energy that exists in the empty space between galaxies. But not all scientists agree with the cosmological constant idea. An alternative theory is known as quintessence, which suggests that dark energy is not constant but can change over time. In this theory, dark energy is a dynamic field that evolves, much like the fields that govern other forces of nature, such as gravity or electromagnetism. To understand this, imagine you're standing at the edge of a calm lake. The surface of the water is smooth, representing the vacuum of space in the cosmological constant model. In the quintessence model, however, imagine that the surface of the lake is rippling, suggesting that the energy of space itself could vary and change as the universe ages. These theories are just two of many that attempt to explain dark energy. The reason we still don't fully understand it is that dark energy behaves in ways that seem to contradict much of what we know about physics. Its exact characteristics remain a mystery. Is it a constant energy? A fluctuating field? Or something else entirely? We're not yet sure. But what we do know is that dark energy is a profound and powerful force that shapes the very fabric of the universe. It is an invisible, pervasive energy that's pushing the cosmos apart, and understanding it may hold the key to unlocking some of the greatest mysteries of the universe. The most compelling evidence for dark energy comes from Type Ia supernovae. These stellar explosions are incredibly bright and can be observed from great distances across the universe. In the late 1990s, two independent teams of astronomers, led by Saul Perlmutter, Brian Schmidt, and Adam Rees, discovered something unexpected. Instead of finding that the universe's expansion was slowing down, as many had assumed, they found that it was actually accelerating. They made this discovery by observing the light from these supernovae. because type Ia supernovae are considered standard candles, objects whose intrinsic brightness we know. Astronomers can measure their distance by comparing how bright they appear to how bright they actually are. This allows us to calculate how fast the universe has been expanding over time. And to their surprise, they found that distant supernovae were farther away than expected. This suggested that the universe was not only expanding but doing so at an increasingly faster rate. This was one of the first major clues that dark energy was driving the acceleration. Another critical piece of evidence comes from the cosmic microwave background, CMB, the faint radiation left over from the Big Bang. The CMB is essentially a snapshot of the early universe, showing tiny fluctuations in temperature that tell us about the distribution of matter and energy when the universe was just 380,000 years old. Using sophisticated instruments like NASA's WMAP, Wilkinson Microwave Anisotropy Probe, and the Planck satellite, scientists have been able to map these tiny fluctuations in detail. What they found was that the pattern of these fluctuations, along with the overall size of the observable universe, supported the idea that the universe is flat and that dark energy is playing a significant role in its expansion. These observations suggest that about 68% of the total energy content of the universe is dark energy, a number that's been confirmed by multiple observations and surveys of the CMB. The CMB not only provides insight into the early stages of the universe, but also reinforces the idea that dark energy is integral to our current understanding of cosmic evolution. In addition to supernovae and the CMB, large-scale structure surveys have provided another crucial piece of the puzzle. These surveys map the distribution of galaxies and clusters of galaxies across vast distances. By studying the way galaxies are spread out in the universe, scientists can gain insights into the expansion history of the cosmos. One such survey, the Sloan Digital Sky Survey, SDSS, has mapped millions of galaxies. By analyzing this vast dataset, scientists have been able to confirm that galaxies are not only moving away from each other, but they are also doing so more rapidly than we expected. This reinforces the idea that the universe is expanding at an accelerating rate, driven by dark energy. Taken together, these key observations, type Ia supernovae, the cosmic microwave background, and large-scale structure surveys, form a compelling body of evidence that points to an accelerating universe. The evidence suggests that dark energy is real and that it plays a central role in driving the cosmic expansion we observe today. It's as if we've caught a glimpse of a hidden force that's been shaping the universe since its earliest moments. And while there's still much to learn, these observations are the foundation upon which our current understanding of dark energy is built. To understand the accelerating universe and the role of dark energy, scientists rely heavily on data gathered by space missions. One of the most significant missions was NASA's WMAP, Wilkinson Microwave Anisotropy Probe, which mapped the cosmic microwave background, CMB, with unprecedented precision. WMAP provided a detailed view of the early universe, helping us understand its structure and composition. The data revealed crucial information about dark energy's contribution to the cosmos, showing us that it makes up about 68% of the universe's total energy. Following WMAP, the European Space Agency launched the Planck mission, which further refined these measurements. Planck's sensitivity surpassed MAPS, providing a more accurate map of the CMB and giving scientists a deeper understanding of the universe's age, shape, and content. These missions were instrumental in confirming that dark energy is a driving force behind the universe's expansion, as well as providing the measurements that support the current cosmological model. Together, WMAP and Planck have provided the most accurate data yet about the very fabric of our universe. While space-based missions like WMAP and Planck offer us a view of the universe from above, ground-based telescopes also play a key role in gathering data about dark energy. Instruments such as the Keck Observatory in Hawaii, the Subaru Telescope in Japan, and the Very Large Telescope VLT in Chile provide detailed images of distant galaxies and cosmic structures. These telescopes allow astronomers to observe the universe in different wavelengths, from optical light to infrared and radio waves. By using these various instruments, scientists are able to gather information about the expansion rate of the universe and measure the distribution of galaxies, further supporting the idea that the universe is expanding at an accelerated rate. In addition to telescopes, specialized observatories dedicated to observing supernovae, such as the Supernova Cosmology Project and the High-Z Supernova Search Team, have been crucial in measuring the universe's expansion. These observatories track type Ia supernovae, which are used as standard candles to measure cosmic distances. The data from these supernovae observations has been instrumental in the discovery of the universe's accelerating expansion. These dedicated surveys provide high-precision data that helps refine our understanding of dark energy's role in cosmic evolution. Together, these data sources, missions like WMAP and Planck, powerful ground-based telescopes, and specialized supernova observatories, form the backbone of our understanding of dark energy. While the tools and methods vary, the combined results tell a consistent story. Dark energy is a real and dominant force in the universe, accelerating its expansion and shaping its evolution. These experiments continue to refine our understanding and will likely lead to even more discoveries about this mysterious force in the years to come. The most widely accepted model for understanding the universe's expansion is the lambda CDM model, also known as the lambda cold dark matter model. This model provides a comprehensive framework for understanding the large-scale structure of the cosmos and how it has evolved over time. In the lambda CDM model, the lambda represents the cosmological constant, which is directly tied to dark energy. The cosmological constant is a term introduced by Albert Einstein in 1917, although he later abandoned it, calling it his biggest blunder. However, when astronomers discovered that the universe's expansion was accelerating in the late 1990s, the cosmological constant was revived as a key component of modern cosmology. In this model, dark energy, represented by lambda, is a constant force that permeates all of space and has the effect of pushing galaxies apart. This constant force remains the same throughout the history of the universe, providing a stable contribution to the universe's accelerating expansion. According to the lambda CDM model, the cosmos consists mostly of three main components: dark energy, around 68%, dark matter, around 27%, and ordinary matter, less than 5%. These proportions are supported by the observations we discussed earlier, including data from the cosmic microwave background and supernovae studies. The lambda CDM model has proven to be incredibly successful in explaining the current state of the universe, but that doesn't mean it's without its open questions. While the cosmological constant is an important part of the standard model, some scientists propose dynamic models of dark energy, which would allow its strength to change over time. One such theory is known as quintessence. Unlike the cosmological constant, which assumes a static and unchanging force, quintessence suggests that dark energy could vary with time and even across different regions of space. In the quintessence model, dark energy is not a constant but a field with an evolving energy density. This field would be governed by its own dynamics, and its effects could differ depending on the point in cosmic history you're examining. Quintessence has its own set of theoretical models that try to explain how dark energy behaves. Some versions of quintessence involve scalar fields, which are mathematical descriptions of fields that can vary across space and time. While these models provide a more flexible approach to dark energy, they also introduce more complexity and require further observational evidence to validate. The debate between the cosmological constant and quintessence is at the forefront of current research in cosmology. Scientists are still trying to determine which model, if any, best explains the observed acceleration of the universe. The cosmological constant has the advantage of simplicity and a solid theoretical foundation, but it raises some deep questions about the nature of dark energy. If dark energy is truly constant, then why is it the exact amount needed to explain the current expansion rate of the universe? On the other hand, quintessence provides an evolving model of dark energy, but it introduces more uncertainties, such as the specific form and behavior of the scalar fields involved. One of the biggest challenges in resolving this debate is the lack of direct evidence for either model. Most of the current data we have comes from indirect observations, like the cosmic microwave background radiation, supernovae surveys, and the large-scale distribution of galaxies. However, these observations only provide glimpses of dark energy's influence, and it's difficult to determine if it's a constant force or a dynamic one. As technology improves and our ability to gather data from more distant corners of the universe increases, we may get closer to understanding the true nature of dark energy. In the quest to understand the universe, cosmologists have two primary models to explain dark energy's role: the static cosmological constant in the lambda CDM model and the evolving dynamic models like quintessence. While the standard model has enjoyed broad acceptance due to its simplicity and observational support, dynamic models offer intriguing possibilities that could radically alter our understanding of dark energy and cosmic evolution. The ongoing debate and research in this area show that even with the incredible progress we've made in cosmology, there's still so much more to discover about the force that drives the universe's expansion. The ultimate truth of dark energy may be more complex and more fascinating than we can currently imagine. To understand how dark energy fits into the bigger picture of cosmic evolution, we need to turn to some fundamental equations in cosmology, the Friedmann equations. These are mathematical equations that describe the expansion of the universe based on general relativity, which is Einstein's theory of gravity. They govern how the scale of the universe changes over time, which is crucial to understanding cosmic expansion. In these equations, the rate at which the universe is expanding depends on various components, such as matter, radiation, and dark energy. Each of these components has a different effect on the universe's expansion. Matter, for instance, slows down the expansion because gravity pulls things together, while radiation, like light, has a similar effect, although it's much less significant in today's universe. But dark energy, which is the most mysterious of these components, does something very different. It accelerates the expansion. One of the key concepts in the Friedmann equations is the scale factor, which represents how distances in the universe change over time. Imagine a balloon with dots on its surface. As you inflate the balloon, the dots move farther apart. The scale factor is a way to measure how far apart those dots are at any given time. In the universe, these dots are galaxies, and as the universe expands, the scale factor grows larger. The rate at which this scale factor changes is determined by the Friedmann equations. Now, dark energy enters the scene in a specific way. In the Friedmann equations, dark energy is represented by a term that contributes to the accelerated expansion of the universe. The more dark energy there is, the faster the universe expands. This effect is characterized by a negative pressure associated with dark energy. Negative pressure is different from what we experience in everyday life. It's a sort of push rather than a pull. It's this negative pressure that counteracts gravity, pushing galaxies apart rather than pulling them together. Let's picture the evolution of the universe as a race. In the beginning, gravity, due to matter and radiation, is slowing the expansion. But as time progresses, dark energy becomes the dominant force, causing the universe to speed up its expansion. This transition is reflected in the Friedmann equations, which show how the different components, matter, radiation, and dark energy, influence the rate of expansion at different stages of the universe's history. In the early universe, when galaxies were much closer together, the effects of dark energy were negligible compared to gravity. But over billions of years, as the universe expanded and galaxies moved farther apart, dark energy started to dominate. The Friedmann equations show that as the influence of matter and radiation decreases, the effect of dark energy increases, causing the acceleration we observe today. So, while the Friedmann equations may seem abstract, they are essential for understanding the evolution of our universe. They provide a framework for how the universe's expansion has changed over time and how dark energy has been driving that acceleration. The key takeaway here is that dark energy, through its influence on the scale factor and its unique negative pressure, plays a central role in shaping the universe's future. It's the unseen hand that is pushing the cosmos outward, ensuring that the expansion continues at an ever-increasing pace. As we delve deeper into the mysteries of dark energy, these equations help us make sense of its role in the vast, ever-expanding cosmos. As we journey through the vast expanse of the universe, we can't help but wonder, how does dark energy affect the grand architecture of the cosmos? From the formation of galaxies to the clustering of superclusters, dark energy is a central player in the evolution of cosmic structures. But its influence is far from simple. To understand this, imagine the universe as a grand cosmic canvas, where galaxies and clusters of galaxies are the brushstrokes. In the early universe, gravity was the dominant force, pulling matter together to form these structures. This gravitational attraction led to the clumping of matter, creating galaxies, stars, and eventually larger clusters of galaxies. However, as time progressed and the universe continued to expand, dark energy began to assert its influence. While gravity continues to draw galaxies together, dark energy works in the opposite direction. It accelerates the expansion of space itself, pushing galaxies apart from each other. This competition between the attractive force of gravity and the repulsive force of dark energy has had a profound effect on the evolution of cosmic structures. While gravity still dominates on smaller scales, keeping galaxies bound together in clusters and groups, dark energy plays a significant role on larger, cosmological scales, where it drives galaxies farther and farther apart. At a certain point in cosmic history, dark energy started to overpower gravity's pull. This shift is why galaxies and clusters that were once bound by gravity began to drift apart. Dark energy, this mysterious force, is responsible for the accelerated expansion that we observe today. But what does this mean for the future of cosmic structures? Will galaxies eventually drift so far apart that they become isolated islands, forever separated by vast stretches of dark, empty space? Perhaps. But the future is filled with multiple possibilities, each influenced by the continued expansion driven by dark energy. The most widely discussed scenario is the Big Freeze, also known as the heat death of the universe. In this scenario, as dark energy continues to accelerate the expansion, galaxies will move farther and farther apart. Stars will burn out, and the universe will cool down, gradually becoming an ever-expanding, dark, and cold void. With no more energy sources available, the universe will approach a state of maximum entropy, where no thermodynamic processes can take place. The Big Freeze is the most likely outcome based on current observations, where dark energy's influence continues to dominate. An even more dramatic possibility is the Big Rip. In this scenario, the acceleration of the universe's expansion caused by dark energy could continue to intensify over time. Eventually, dark energy's power would be so great that it would tear apart galaxies, stars, and even atoms themselves. The fabric of space-time would be ripped apart in a cataclysmic event, leading to the ultimate dissolution of all matter. Though this scenario is highly speculative, it highlights the immense potential power of dark energy and its capacity to shape the universe's fate. On the other hand, some theorists propose cyclic models, where the universe goes through cycles of expansion and contraction. In these models, dark energy's effects might eventually reverse, leading to a big crunch, where the universe collapses back in on itself. After this collapse, a new Big Bang could occur, and the cycle would begin anew. While this model is intriguing, it's less supported by current observations, especially with the discovery that dark energy is causing an accelerated expansion, making such a collapse seem less likely. As we ponder these potential futures, it's important to remember that the universe is an ever-changing, evolving system. While dark energy continues to drive the expansion of the cosmos, it is only one piece of the cosmic puzzle. The future of the universe remains uncertain, shaped by the interplay of dark energy, gravity, and other forces yet to be fully understood. In the end, whether we face a big freeze, a big rip, or a cyclical rebirth of the cosmos, one thing is clear: dark energy will continue to play a central role in shaping the fate of the universe. Its elusive nature, while mysterious, is the key to understanding not only the past and present of our cosmos, but also the very nature of space and time itself. The cosmic evolution of galaxies, clusters, and the universe as a whole is a tale of balance between opposing forces, gravity and dark energy. Each has its own influence on the way structures form, evolve, and ultimately dissipate. As we continue to explore the mysteries of dark energy, we unlock more answers to these cosmic questions, revealing the intricate tapestry of our ever-expanding universe. As we delve deeper into the enigmatic force that is dark energy, we are confronted with not only scientific questions but profound philosophical ones as well. What does the very existence of dark energy tell us about the nature of reality? Does the fact that the universe is expanding faster and faster suggest that it has an inherent purpose? Or is it merely a cosmic accident, driven by forces beyond our comprehension? Dark energy raises fundamental questions about the essence of existence itself. If the universe is accelerating toward an eventual end, where does that leave us as conscious beings? Are we part of a grand cosmic design, or are we simply fleeting observers of a universe that is ever-shifting, expanding, and ultimately heading toward some distant fate? The fact that dark energy seems to be working against gravity, the very force that binds matter together, forces us to question the underlying unity of the cosmos. Is the universe inherently chaotic, governed by opposing forces that ultimately lead to an unending state of flux? Or is there a hidden order, a deeper balance that we have yet to understand? Could dark energy be the universe's way of reaching some unknown, higher state of being? Or is it simply an unstoppable force with no greater purpose, pushing everything toward an inevitable end? Dark energy also provokes a deeper contemplation of time itself. Time, as we understand it, is a flow from past to present to future, with each moment giving birth to the next. But what happens when the expansion of the universe accelerates so quickly that even time itself seems to stretch and distort? What do we really mean when we speak of the future if dark energy is pushing the universe in a direction that seems irreversible? The accelerating expansion of the cosmos could ultimately stretch time out to such extremes that galaxies, stars, and even atoms might become isolated, each in its own distant corner of the universe, with no hope of ever interacting again. In such a future, what would time look like? Would it lose its meaning if all that remains is a cold, empty void, where the passing of moments is nothing more than the continued expansion of space itself? Or could dark energy somehow reveal a new aspect of time that we can't yet comprehend, an ever-deepening journey towards something unknown, a timelessness that transcends the boundaries of our understanding? The ultimate fate of the universe is perhaps the most profound philosophical question that dark energy brings to the forefront. What will happen to everything we know? The stars, the galaxies, the very fabric of space-time, if dark energy continues its relentless march toward an ever-accelerating expansion? Will the universe experience a gradual fading into darkness, with stars burning out and galaxies drifting apart? Or could there be a moment of cosmic revelation when the true nature of dark energy is unveiled, unlocking new possibilities for the future of the cosmos? In this sense, dark energy acts as a reminder that the universe is not static. It is evolving, changing, and potentially heading toward a future that we can't predict. And perhaps most importantly, dark energy challenges our perception of permanence and meaning. If the cosmos is destined to expand forever, what does that say about our place within it? Are we simply a temporary blip in an eternal cosmic journey? Or is there something more, a deeper significance to our existence in a universe that seems to be constantly moving toward something unknown? Is the universe's fate intertwined with our own? Or do we merely witness the cosmic process as passive observers, our lives too fleeting to matter in the grand scheme of things? In many ways, dark energy forces us to confront the limits of our own understanding. It challenges our belief that we can ever fully grasp the forces that shape the universe, and it presents us with a paradox. The more we discover about the cosmos, the more we realize how little we truly know. This endless pursuit of knowledge, driven by the mysteries of dark energy and the cosmos itself, invites us to reflect on the nature of purpose in our own lives. As human beings, we seek meaning in the vastness of the universe. We long to understand our place in the grand cosmic scheme, to uncover the hidden forces that govern our lives. And yet, as dark energy continues to accelerate the universe's expansion, we are reminded of the ultimate unknowability of the cosmos. The universe is constantly evolving, and we, too, must evolve with it. In this sense, dark energy not only shapes the fate of the universe but also reflects our own constant search for purpose, meaning, and understanding in an ever-changing world. In the end, dark energy is not just a scientific concept. It is a philosophical inquiry that challenges our perceptions of existence, time, and the ultimate fate of the cosmos. It invites us to contemplate the deeper questions of the universe, urging us to consider the nature of the forces that shape our world and our place within it. As we continue to explore the mysteries of dark energy, we are reminded that the search for meaning, knowledge, and understanding is a journey that transcends the boundaries of time and space. And perhaps, in the grand expanse of the cosmos, it is the very search itself that gives our lives meaning. Despite decades of research and observation, dark energy remains one of the most profound and baffling mysteries in modern astrophysics. It's a force that shapes the fate of the universe, accelerating its expansion, yet it's invisible to all our instruments. We cannot detect it directly. We can't touch it, taste it, or even see it in the traditional sense. And yet we know it's there. It's not just a theoretical concept. It has a tangible effect on the cosmos, propelling galaxies apart at increasing speeds. The elusive nature of dark energy is what makes it so intriguing. Unlike other forces that we've come to understand, like gravity or electromagnetism, dark energy doesn't behave in ways we can easily observe or measure. It doesn't leave behind direct clues like other phenomena in the universe. It's not like the force of gravity, which you can feel when you jump and fall back down to Earth. Dark energy is pervasive, affecting everything on the grandest scale, but it doesn't interact with matter in any way that we can directly perceive. Why does it remain so mysterious? One reason is that dark energy operates on a scale that is far beyond our usual experience. We live on Earth, a small speck in the vast cosmos, where gravitational forces dominate. Dark energy, on the other hand, is a force acting on the universe itself. Its effects noticeable only when we observe the universe as a whole. This grand scale of influence is beyond our everyday understanding, and our instruments, though powerful, still aren't equipped to grasp it fully. To unlock the secrets of dark energy, scientists have turned to some of the most sophisticated missions, telescopes, and experiments ever created. These efforts are pushing the boundaries of what we know about the universe and dark energy's role in its expansion. One of the most significant current efforts is the Dark Energy Survey, DES, an international collaboration aimed at mapping the universe's large-scale structure. By analyzing galaxy clusters and the distribution of galaxies across vast distances, DES is working to map the universe in greater detail, allowing scientists to study how dark energy impacts the large-scale structure and the cosmic expansion. The results from this survey are helping to refine our understanding of dark energy and its relationship to the universe's growth. Another major mission is ESA's Euclid mission, set to launch in the near future. This space telescope will be equipped to observe the geometry of the dark universe, investigating the nature of dark energy and dark matter. With its advanced instrumentation, Euclid will help map the shapes and distributions of galaxies, shedding light on how dark energy influences the cosmic fabric. The James Webb Space Telescope, JWST, launched in December 2021, is also playing a crucial role in unraveling the mysteries of the universe. Though its primary focus is the early universe and the formation of galaxies, its observations of the cosmos' oldest light may provide crucial insights into the dark energy that has shaped cosmic evolution over time. The JWST's ability to observe distant objects with unparalleled precision might reveal patterns of expansion that could lead us closer to understanding dark energy. While observational efforts like these are essential, they go hand in hand with theoretical advancements. Scientists continue to develop new models and refine old ones to explain the behavior of dark energy. The cosmological constant, lambda, first introduced by Einstein, is the most widely accepted model, which sees dark energy as a constant, uniform force that acts against gravity. But alternative theories, like quintessence, propose that dark energy could be dynamic, changing over time and space. The challenge for cosmologists is that these models are not mutually exclusive. Theories about dark energy are still being debated as researchers try to identify which model best fits the evidence. Some are focused on understanding whether dark energy is truly constant or whether it might change over time or even have varying effects on different parts of the universe. Recent breakthroughs in quantum field theory and advanced cosmological simulations also hold promise for explaining the elusive nature of dark energy. As we refine our understanding of the fundamental forces that govern the cosmos, we may discover new theories that open the door to explaining dark energy in a more concrete way. Despite the progress made so far, the true nature of dark energy is still largely beyond our reach. The technology to detect it directly or fully understand its behavior doesn't yet exist, and we are still grappling with the deep complexities of its existence. But the pursuit to unravel dark energy's secrets is far from over. Each discovery and observation moves us one step closer to understanding this cosmic force and how it will shape the future of the universe. As new missions and experiments continue to provide more data, scientists are hopeful that in the coming decades, we may have a clearer picture of what dark energy truly is. Will it lead us to a new understanding of the cosmos? Could it be the key to unlocking the ultimate fate of the universe? Only time and the relentless curiosity of humanity will tell. For now, dark energy remains as elusive and mysterious as the day it was first theorized. It challenges our understanding, stirs our imaginations, and propels the quest for knowledge forward. As we continue to explore the cosmos, dark energy will remain at the heart of our search for answers, pushing the boundaries of science and philosophy alike. And perhaps, in the end, it is this very mystery, this unknown force, that will ultimately reveal the most profound truths about our universe and our place within it. Dark energy does not exist in isolation. In fact, it's intrinsically connected to several other cosmic puzzles, forming a complex web of mysteries that scientists are trying to untangle. Each of these puzzles, such as dark matter, cosmic inflation, and the pursuit of a unified theory of physics, interacts with and potentially explains some aspect of dark energy, or vice versa. Together, they form the backbone of modern astrophysics and cosmology, urging us to think more deeply about the very fabric of our universe. One of the most significant connections is between dark energy and dark matter. While dark energy accelerates the expansion of the universe, dark matter, on the other hand, exerts a gravitational pull and is responsible for the formation of galaxies and large-scale structures in the universe. Though they have opposing effects, one pushing the universe apart and the other pulling things together, both dark energy and dark matter are believed to make up about 95% of the universe. The fact that these two invisible forces seem to balance out the universe in such a profound way raises intriguing questions about how they interact with each other. Are dark energy and dark matter part of a more profound, unified theory? Could they be two sides of the same coin, perhaps influenced by similar fundamental principles that we haven't yet uncovered? As we study dark energy, the nature of dark matter also takes center stage, offering a deeper understanding of the fundamental forces that shape our universe. Another key connection is with the concept of cosmic inflation, the rapid expansion of the universe just after the Big Bang. Cosmic inflation helps explain the large-scale uniformity of the universe and the formation of the structures we see today. Some theories propose that the same energy responsible for inflation might be related to dark energy, suggesting that the force driving the accelerated expansion of the universe today could be linked to the same mysterious mechanism that set the stage for the universe's creation. The similarities between the two forces are striking. Both cosmic inflation and dark energy are thought to act on the universe as a whole, shaping its evolution on the grandest scales. Some physicists even hypothesize that understanding the mechanics behind cosmic inflation might unlock the secrets to understanding dark energy, helping us connect these two key moments in the universe's timeline, its birth and its ongoing expansion. Ultimately, dark energy's elusive nature is just one piece in the larger quest for a unified theory of physics, one that can explain all the fundamental forces of nature under a single framework. Right now, we have two dominant theories that describe the universe: general relativity, which explains the force of gravity, and quantum mechanics, which governs the behavior of particles on the smallest scales. However, these two theories don't fully mesh, especially when we try to apply them to phenomena on the scale of the cosmos, like dark energy. In this search for a unified theory, dark energy plays a pivotal role. Its mysterious properties challenge both quantum mechanics and general relativity, urging physicists to rethink our current understanding of the universe. Some theories, such as string theory and loop quantum gravity, attempt to bridge the gap between these two paradigms and potentially offer insight into the nature of dark energy. If dark energy can be understood in the context of a unified theory, it might reveal fundamental truths about space, time, and the very structure of reality itself. The quest to understand dark energy is thus not only about unraveling one cosmic mystery. It's a journey that could bring us closer to unlocking the ultimate laws of nature, paving the way for a new era of scientific discovery. In the grand scheme of cosmic exploration, dark energy is not just a puzzle on its own. It's a piece of a much larger picture, one that connects with dark matter, cosmic inflation, and the ongoing search for a unified theory. As we continue to investigate dark energy and its relationship to other cosmic phenomena, we may soon discover that the answers to these mysteries are intertwined in ways we have yet to fully comprehend. The quest for knowledge is ongoing, and dark energy is at the heart of this journey, a force that could one day help us understand the universe in a way we never thought possible. As we continue our journey through the mysteries of the cosmos, let us pause for a moment, allowing the vastness of the universe to settle within us. Imagine, if you will, the endless stretch of space, stretching beyond comprehension, yet subtly interconnected. In this quiet moment, we're reminded that even in the vastness, there are forces, unseen, unfelt, that drive the universe forward, shaping its fate in ways we can barely understand. Dark energy, this elusive force, has been with us since the beginning. It is the force that pushes the cosmos outward, yet it remains beyond our reach, shrouded in mystery. How can something so intangible, something we cannot touch or see, hold such power? Think of the universe as a great ocean. Each galaxy, each star, each planet is a tiny island. The ocean may seem still at the surface, but beneath it, invisible currents move the water in ways we cannot always detect. Dark energy is like one of these deep, hidden currents, shaping the flow of the cosmos in a direction we cannot always predict. What would it feel like to witness the expansion of the universe, to stand at the edge of time and space, knowing that the universe is stretching farther away, faster, as though it is reaching for something beyond? Could the future of the cosmos be determined by something as invisible as dark energy? In this quiet moment of reflection, let us consider the questions that dark energy presents to us. Could it be that, in the end, the universe is forever changing, always moving away from us, never to return to its original form? Will we one day see the end of the cosmos in the Big Freeze? Or could there be another possibility, one where the universe cycles in a grand eternal rhythm, forever reborn? Close your eyes for a moment and envision the universe, vast and silent, slowly expanding. The stars and galaxies drifting apart, not out of force, but out of an unspoken need to stretch further, to grow. And somewhere in the shadows, dark energy moves, quiet, invisible, but ever-present. This cosmic dance of expansion, what if it's not a random event, but part of a deeper, more profound purpose, one that we are only beginning to understand? As we gaze into the night sky, do we feel the pull of dark energy beneath the stars, guiding the universe toward its ultimate destination? How does it feel knowing that we are not just passive observers, but active participants in this unfolding mystery? Our understanding of dark energy, the universe, and our place in it is still evolving. With every discovery, we come closer to grasping the threads that connect us all to the cosmos. As we near the end of our journey through the universe's darkest mysteries, let us remember that there are still more questions than answers. But it is through these questions that we find meaning, and through reflection that we deepen our connection to the vastness of the cosmos. Allow the mystery to linger, like a soft whisper in the infinite silence of space. And in that silence, may we find peace, knowing that the journey of discovery is just as important as the answers themselves. As we come to the end of our exploration into the universe's darkest mysteries, let us take a moment to reflect on the journey we've shared together. Through the vastness of space, through the shadows of dark energy and the expansion of the cosmos, we've uncovered just a glimpse of the infinite complexities that shape the very fabric of our universe. It's truly remarkable, isn't it? How much we still don't know. How much of the cosmos remains a beautiful mystery just beyond our reach. And yet, in the unknown, there is a certain wonder, a peace that comes from embracing the questions, the vastness, and the mystery of existence itself. Dark energy, so elusive and intangible, continues to challenge our understanding of reality. But perhaps the beauty lies not in the answers, but in the very pursuit of them. It's a journey that invites us to look up, to wonder, and to appreciate the vastness of the universe we are a part of. As you reflect on the cosmos, on dark energy, and on the unfolding story of the universe, let yourself be filled with a sense of awe. We are all part of this incredible adventure, spinning through space, bound together by forces both known and unknown, as we move ever forward into the future. Now, as the journey comes to a close, may you feel a sense of tranquility in the mysteries we've explored. Let the quiet expanse of space and the wonder of the unknown settle gently in your mind, bringing you peace as you prepare for whatever lies ahead. Take a deep breath and allow yourself to relax. Let the soothing rhythms of the universe flow over you as we close this chapter. The mysteries we've uncovered today are only the beginning. There is much more to explore, to wonder about, and to discover. Thank you for taking this journey through the cosmos with us. May the wonder of the universe stay with you, filling your heart with calm and curiosity. Until next time, keep looking up, and may your thoughts be peaceful as the stars continue their eternal dance. As we wrap up our deep dive into the universe's most profound mysteries, let's pause and reflect on the key ideas we've uncovered about dark energy and cosmic expansion. We began by exploring the vastness of space and the strange, invisible force, dark energy, that accelerates the universe's expansion, pushing galaxies farther apart with each passing moment. This mysterious force, making up about 68% of the cosmos, remains one of the greatest enigmas in modern astrophysics. Its existence challenges everything we thought we knew about gravity, space, and time. From the groundbreaking discoveries of cosmic expansion, led by Edwin Hubble, to the game-changing observations of Type Ia supernovae in the 1990s, we've come to understand that the universe is not only expanding, but doing so at an ever-increasing rate. This acceleration, driven by dark energy, reshapes the way we view the universe's past, present, and future. As we delve deeper, we discovered that dark energy isn't just an abstract concept. Its influence permeates all of space, shaping the very evolution of the universe. Whether it's through the cosmological constant or more dynamic theories like quintessence, dark energy forces us to rethink the nature of reality itself. The evidence from supernovae, the cosmic microwave background, and large-scale cosmic surveys continues to paint a picture of an ever-accelerating universe. And yet, with every discovery, we are left with even more questions. Why does dark energy exist? Is it a constant force, or does it evolve over time? What will it mean for the future of the cosmos? These are questions that challenge us, beckoning us to look deeper into the very fabric of space and time. Ultimately, these cosmic mysteries invite us to reflect on our place in the universe. They remind us that we are part of a grand, ever-changing cosmos. A cosmos full of unanswered questions, yet full of beauty and wonder. As we continue our search for answers, we must embrace the unknown with curiosity and humility, knowing that with each discovery, we uncover just a little more of the infinite. In contemplating the unknown, we are not just exploring the universe, we are also exploring ourselves and our place within this vast, interconnected cosmos.